Hi there, Dr. Deshawn here. And in this video, we're going to talk about functions, a topic you would study in a mathematics algebra class. We're going to talk about functions, the definition of functions, operations with functions, and we are going to do a lot of examples that you might see in an algebra class. So let's start with the definition of a function. So if you'll look over here on my smartboard screen, I've got the definition up. A function f from set A to set B is a relation that assigns the x elements in set A to exactly one element y in set B. It is a one-to-one correspondence. Every element in the domain, the x's, is mapped to exactly one element in the range, the y's. So the x's are the domain, also called the input values. The y's are the range, also called the output values. It's a one-to-one correspondence. Remember, for every value x that goes in, you're going to get exactly one element y coming out. So before we actually start to do the algebraic examples, let's take a look at the graphic representation, the picture up here on the screen, so we can just get an idea in our head of what the concept and how the definition works. So up here on the screen in the blue box, we have the time of day, and the time of day in PM, in the afternoon hours, 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, 5 o'clock, 6 o'clock in the blue box. And then in the yellow box over here is the temperature in degrees Celsius. So they're mapping at each hour on the hour what is the temperature, and you have a different variety of numbers that here represent the temperature. So the time of day, that's the domain, those are the x's, the temperature, that's the output, those are the y's, that's your range. All right, so what does this say? This is saying this is a representation of a function. At 1 o'clock, it is 9 degrees Celsius, okay? All right, and then at 2 o'clock, it is 13 degrees Celsius, one-to-one correspondence. At 3 o'clock down here, 15 degrees Celsius, all right? Now take a look at what happens at 4 o'clock. 4 o'clock, it is still 15 degrees Celsius, okay? So now that 15 in the y box over here, the output value is taken on two x values, that's okay, all right? So that's okay because as long as the x's are going to one place, we're good, okay? You can't have the x's going to two places. At 4 o'clock in the afternoon, it can't be 15 degrees and 17 degrees at the same time. You can't have that, okay? So that's why, so function, every element in the domain is being mapped exactly one place, okay? At 5 o'clock, it's 12 degrees Celsius. At 6 o'clock, 10 degrees Celsius. That is what the concept of a function is. For every x, there's exactly one y. For every input, there's exactly one output, right? For every element in the domain, there's exactly one element that it's going to match in the range. It's a one-to-one correspondence. That's the concept of a function. Now, let's take a look at what you might be using in an algebra class. We're going to do some examples now, algebraic examples. We're going to evaluate functions, and we're going to go through some operations. You can add functions, we can subtract functions, multiply functions, divide functions. We can also do a composition of functions, all right? So you learn in elementary school, you got 4 operations. You can add and subtract, and you can multiply and divide. And so you learn that when you're young. When you get to an algebra class, when you start studying functions, really we've got 5 operations with functions, don't we? Okay, so we can add them, we can subtract them, we can multiply, divide. Composition, all right? Composition is when you actually plug a function into another function. So we're going to take a look at all these operations, and we'll take a look at an actual application of a composition, so you can see how in real life you might actually ever think about it and use it. So let's take a look at the examples here. Example 1, I'm going to use 3 functions in an example. Within example 1, I have my f function. F function I'm going to define as a radical function. F function is going to be radical quantity 4x minus 3. G function, we're going to define that as a quadratic. So the G function, we're going to define that as 5 minus x squared. H function is going to be a series of ordered pairs. So for the H function, we're going to use negative 2, 3, 1, 5, 5, negative 4, and 7, 6. We're going to use these ordered pairs for the H function. Okay, so let's go ahead and get started. Letter A. So letter A, to evaluate a function, okay, the basic concept, evaluate a function, we want to take f, the function f, and we want to evaluate it when the x is 7. okay? So our f function, now what was our f function again? Well, our f function, right, what did it tell us to do? It was the radical expression. It said take 4 times x and subtract 3. That's what our f function is. Now, evaluating functions. How do we evaluate functions? Well, it's basically just a substitution. It's a substitution. We are going to take the f function, and in place of the x in the function, we're going to take the x, we're going to replace it with 7. You're just going to make a substitution. So our f function is 4 times quantity minus 3. That's what our f function is. But instead of putting the x's in the f function, we want to take the x and we want to take the x and substitute 7 for the x. That's how you evaluate a function. All right, and then we'll do the computation. So what is f of 7? F of 7 is going to be, well, 4 times 7, we're under a radical here. 4 times 7 is 28. 28 minus 3 is 25. So this is what my f of 7 is. And we can take the square root of 25. So what is f of 7? Okay, when you take the square root of 25, you get positive 5, right? We want the positive root of 25. The positive root of 25 would be a positive 5, all right? And that's it, all right? Now, sometimes my students, get a little bit turned around with this, and they said, well, taking a square root, don't we have to have plus and minus? So that's involved when you're solving quadratic equations, but not when you're taking a positive root, all right? And second of all, remember that we're working functions. By definition, a function is a one-to-one correspondence. For every x you put in, you're going to get one y value, okay? You're only going to get one y value, so just the positive root of 5. What did we do here? We determined that on the f function here, when x is 7, y is 5, right? They gave us the input, they gave us the x, the domain value. We give them the output, the range, the y value. So this is what we were working out here, okay? So they basically, with functions, with the way we're working it with these examples today anyways, they're telling you the x, and your job is to tell them the y. They give you the x, you give them the y, all right? They're giving you the input, you're giving them the output, and this is how you go through, work through that, all right? Let's take a look at some operations now. We want to take g plus h of -2. So by definition, we want to add functions together. So we have g plus h of -2. We're going to write it in separately. We want to take the g of -2. We want to add it to h of -2. That's the definition. So that's what we want to do first. We want to pull it apart. We want to do the addition. Right? G of -2, just exactly the way we evaluated over here, but we're going to go to the g function and replace the x's with -2 in the g function. So my g function, I have 5, I'm going to just group it together, minus, and I'm changing the x to a -2, all right? And then I have subtracting again, and I'm changing that x again to -2, all right? So what we want to do with the g function, all right, with the g of -2, so you want to take the x's in the g function and change them to -2, right? What about h of -2? What do we do with h of -2? Well, let's look at our h function, but it's a series of ordered pairs. So how do we answer this? Well, h of -2, remember, in the parentheses, they're telling you the x, right? So h of -2, they're telling you the x, your job is to give them the y. On the h function, when x is -2, find where the x is -2. When x is -2, what is the y coordinate? It's 3. H of -2 is 3. They're telling you the x, you're telling them the y. They're giving you the input, you're giving them the output. All right, now we have to compute this one because the g function, so we do have to compute. So when you do compute this, order of operations, correct? So we have to evaluate the exponent first, okay? So you have 5, all right, minus a -2, I'm going to put +2. All right, and then I'm bringing this minus down because I have to do order of operations first. I have to take the -2 and square it. -2 times -2, 4, and then I have that negative out front to apply to this. All right, and then +3. So I'm here with my numbers, and so when I combine these, 5 plus 2 is 7. All right? 7 minus 4 is 3. 3 plus 3 is 6. My final answer for example letter B here is 6, all right? So here's how you would add functions, and here's how you could evaluate with a quadratic and using a set of ordered pairs. So these are the first two. We're going to do one of each, so I have a lot more examples. I'll need to erase these two. All right, I'm going to put two up at a time. So let me erase these two. Let's take a look at example C and example D. So example C will be a subtraction example. Example D will be a multiplication example. So letter C, let's do a subtraction example. So for letter C, let's take a look at f minus g of 3. So f minus g of 3. All right, that's a cursive f. I do that sometimes, okay? And then letter D, g times h of 5. So letter D would be g times h of 5. All right, so let's take a look at here. All right, so subtraction example, and here I'll make this uncursive. Okay, so you know, okay, so there's f minus g of 3. So by definition, we want to call this f of 3 minus g of 3. Okay, that's what definition. All right, so we want to call this f, and then we want to evaluate each piece separately and combine them. So f function is your radical function. So the f function, so under the radical we have 4 times x minus 3, and we want to replace the x. So the f of x is 4x minus 3 under the radical, right? So f of 3, well, we want to replace the x with 3. All right, minus now g of 3. Okay, g of 3, don't forget grouping symbols. That's what you have to be careful of when you subtract functions. Don't forget grouping symbols, because my g function has 3 terms, so I need to subtract each of the 3 terms. I will need to distribute the subtraction. All right, so use grouping symbols. And now, so what do we have for g of 3? It's going to be 5 minus substitute 3 minus substitute 3 again and square it. All right, so we're here. All right, so f of 3, you replace the x with 3 in the f function. G of 3, you replace the x with 3 in the g function. Once you do that, now we compute, okay? 4 times 3 is 12, 12 minus 3, so we have radical 9 here, minus. Now you gotta be careful with this, because order of operations again, we have to evaluate the exponents before we can do the other operations. So we still have the 5 minus 3 squared is 9. Order of operations, evaluate the exponents. All right, square root of 9 is 3, just positive 3, okay, because we're evaluating functions, it's just one correspondence, minus, and then inside the parentheses, right, it's order of operations. So after we do the exponents, let's evaluate the parentheses. 5 minus 3 is 2, and then 2 minus 9, that's a negative 7. All right, so, and then 3 minus a negative 7, so this final answer, this subtraction problem gives us 10. All right, so we have 10 for this answer here. All right, so subtracting functions. Subtracting, you have to be careful, because that second term, right, that you're subtracting, that second function, grouping symbols. Use grouping symbols, because if you do have more than one term that you're subtracting, you're going to have to distribute the negative sign, okay? Distribute the negative sign, or you just have to make sure that you're, I worked order of operations in here, but you just want to be careful. You want to make sure you're careful with that. All right, letter D, multiplication. So let's go ahead and multiply, all right? So multiply the functions. So we want to essentially take g of 5, all right? And we want to multiply this by h of 5, multiplication of functions. All right, so just multiply, you evaluate each one separate and multiply them. So g of 5, okay, so that's going to give us what? It's going to give us 5 minus, replace the x with 5, minus, replace this x with 5 squared, okay? So g of x, this is what g of x is. G of 5, you're going to replace the x's with 5's, okay? What about h of 5? What about h of 5? That's the ordered pairs, okay? How does that work? H of 5 with the ordered pairs, well, you know, the h of 5, they want you to replace the x with 5, all right? So replace the x with 5, all right? So when x is 5, go to the h function. When the x coordinate, not the y, when the x coordinate is 5, what is the corresponding y coordinate? Well, you can see here, it would be -4. Okay, so -4, that's the corresponding y coordinate. All right, and then so order of operations in here, so we compute this, we have 5 minus 5 minus 25. Okay, order of operations, exponents before you use the other operations, that will be multiplied by -4. Work in the parentheses here, so 5 minus 5 is 0, so we have -25 being multiplied by -4. Negative times a negative, that gives us a positive 100, okay? So here is our answer for the multiplication example, all right? So multiplying functions, a different variety of multiplying functions, all right? So here's our example of multiplication of functions. All right, so let's take a look at a division and composition now. So division and composition, so we evaluated a function, we addition, subtraction, multiplication. Let's look at division and a composition, and then we'll do our application example. So let me erase here, so we can get a couple more on the board in this space. We're gonna take a look at a division and a composition, and then we'll do the application. So division first, the division example, letter E, f over h of 1. So this is letter E. We're going to put f over h of 1, all right, for letter E example. In our letter F example, let's do a composition here, h composed with f of 7. So h composed with f of 7. So let's take a look at these operations. All right, so we have a division and we have a composition. All right, so let's look at the division. So we can rewrite this and we can call this f of 1 over h of 1. All right, and then we just need to evaluate the numerator and the denominator. We just need to evaluate each one. So f of 1, well, the f function is our radical function. We want to just write our radical function down, but we want to replace the x with 1. So your numerator, you're going to have radical, and you're going to have 4 times 1 minus 3. There's the numerator. The denominator, we want h of 1. The h function is your ordered pairs. All right, how does this work? Okay, they're telling you the x, when the x on the h function, when x is 1, what is y? So you go to the h function, when x is 1, here's where x is 1, what is the y coordinate? It's 5. Okay, so it's 5. And then we need to just compute the numerator. So compute the numerator, so you have under the radical, 4 times 1 is 4, 4 minus 3 is 1, the square root of 1 is just 1, so this answer would be 1/5 fraction. Okay, so 1/5. And that's division of functions. Okay, so you just evaluate the numerator, denominator, and division of functions. All right. And finally, the extra operation that we have here, right? Because we can add functions, subtract, multiply, divide, but we can also do composition, right? This is h composed with f of 7 is how it's read. So we will rewrite this as h of f of 7. Okay, h of f of 7. All right, I have the definition written here of composition of functions. So composition of functions is basically, it's telling you you're going to plug a function into another function. That's what it is. You take one function and substitute it into another function. So that's what composition is. All right, now how do we actually evaluate this? You're going to work from the inside to the outside. Okay, we take care of the f of 7 first. Work from the inside to the outside. That's how composition works. So we have the h of, right, f of 7. So you go to the f function, which is the radical expression, and plug in 7. So 4 times 7 minus 3. So leave the outside alone. You're going to work the inside first. You're going to work from the inside to the outside. Evaluate the inside function first. When you're done, plug that into the outside function. Okay, so we have h of, let's see, 4 times 7 is 28. 28 minus 3 is so 20, radical 25. So square root of 25 is positive 5. We're just taking the positive roots, so this is h of 5. All right, so you're plugging a function into a function. You evaluate the inside first. Once you're completely done evaluating the inside, take care of the outside. What does the outside want us to do? H of 5. What is h of 5? Go to the h function when x is 5. When the x is 5, what's the y coordinate? It's -4. All right, so that's this different operation that's applied to functions. We can do composition of functions. We can plug a function into another function. All right, so here's your basic examples demonstrating each of your operations here first. Okay, I'd like to do one more example that's more of an application. What would we ever, a lot of my students will ask, composition, where am I going to use this outside of a math classroom? So I want to take a look at a quick application problem. The application problem, I'm going to put it up here on the smart board so we can read it and see the words there. We'll work it out on the front board. So I'm going to walk over here and set up the application problem for composition of functions. Okay, so let's take a look at this. And we're going to take a look at an application problem so we can do a composition of functions with this application problem right here. So, and it's about a computer. And so if we can see it all right here. So there's companies selling computers and they're having a sale, right? And so if you can see the problem on the screen okay over there, a manufacturer of a computer company is offering 2 discounts on last year's model of computer. I guess they want to out with the old and in with the new. So they want to sell off last year's model of computers, and they are offering 2 different types of discounts. Okay, so both they can be used on the computer you're buying. They're going to give you a $200 rebate on the computer, and in addition to that, 20% off. So you have a $200 rebate and 20% off. Okay, so the ultimate question is, when you buy your computer, do you apply the rebate first, then the 20% off, or do you apply the 20% off first, then take the rebate? Which one do you do? That's what a composition is. It's applying a function to a function where you have to do one at a time. Okay. Now, composition of functions is not commutative. Addition and multiplication is commutative. You can take 2 numbers, 5 plus 3 is 8, 3 plus 5 is 8, and it doesn't matter which way you do that. But composition of functions is not commutative. So one way is going to save you more money than the other way. And you should walk in to any store when you're purchasing these things with the knowledge of how the mathematics works, and you should not rely on the people that are selling, the salespeople, to do that for you, because sometimes they get it right and sometimes they don't. So especially if you're buying a bigger, like a car or something, if that happens all the time, they give you a rebate and a discount. Which one do you apply first? You want to make sure that you know your math so you can take care of that. So let's take a look at this. Okay, so let's take a look at this and let's see which one. Is it the rebate first or the discount? And the answer, it's just going to be different. It depends on how much is the rebate and how much is the discount. All right, so for this particular problem, based on these numbers, let's see what works in this situation, but it's not what's going to work all the time, right? You just have to crunch the numbers when you're doing that. So this is example 2, okay? So letter A wants us to write the function that represents the rebate, okay? What is the price representing the rebate? So I'm going to call this letter A and I'll write rebate. All right, and they want us to write function F. Function F, and I'm going to write function F in terms of P. My independent variable is going to be the price of the computer. So I want to write something in terms of P that represents what is the price of the computer after the rebate. Okay, so whatever the computer costs, if the computer costs $1,000, okay, $1,000 for the price of the computer, but they give me a $200 rebate, that means I'm going to take the price $1,000 of the computer, I'm going to subtract the $200 rebate, and I would pay $800 if it was just the rebate by itself. So in terms of writing a formula for this, if I'm applying the rebate to the price of the computer, I would take the price of the computer and I would subtract the $200 rebate, and that would give me my sale price if it was only the rebate being applied to it. Okay, so letter B says, what if it's just the discount being applied? So what if it's just the discount? So the discount, so we want to use the G function to represent the discount. So the G function, so write a function G that represents the sale price if the 20% discount applies. Okay, so 20% discount. So I have my $1,000 computer here but they're trying to get rid of them. If only the 20% discount applied, then I can take the discount 20% off. Well, so if I'm saving 20%, that means I'm paying 80%. So what is the price that I would actually pay for the computer? If I have a 20% discount, then I'm actually going to pay for 80% of the computer. 80% written as a decimal is 0.80. So I'll call it 0.80 times P. So if I'm saving 20%, subtracting 20%, that means I'm paying 80%. I'm going to write it like this, okay? So if only the rebate applies, then I'm going to take the price of the computer and subtract $200. If only the discount applies, I'm going to take the price of the computer and multiply it by 0.80, 80%, because I'm paying 80% with a 20% discount. Now, letter C is asking you to involve both at the same time now, like the store is offering, okay? So they want you to do composition, right? So they want you to take the F, composition with G, and they want you to take the G, composition with F, and they want you to tell you which one's going to be the better deal. And they won't come out the same. One of these will be the better deal, all right? So let's start with the F composition G. This means, by definition, that you're taking the F of G of P, because it's the price of the computer, okay? So you work from the inside to the outside, and because you work from the inside to the outside and G happens to be the discount, this one you're applying the discount first, okay? So this one is, so the G function is your discount. So this is discount first, then rebate. Okay, so this is discount first and then rebate. All right, so let's go ahead and compute that. So you have F of, now G of P, so that's going to be 0.80 times P, all right? And now we're going to plug this into the F function. Now remember how this works with variables, especially the F function. Well, all you're going to do is we're going to replace the P with 0.80 P and then subtract $200. Okay, so this is the expression that we have, and we'll plug in numbers in a minute to see which one works better. But this is when you're dealing with the discount first, okay, and then you're applying the rebate. What if it's the other way around? Okay, what if they want you to do G composition with F? This means G of F of P. Okay, so that's what this means. Okay, so by definition, this means G of F of P. You know that we work from the inside to the outside. The inside is the F function, so this one is applying the rebate first. Okay, so this is rebate first, then discount. Just so we can see which one is going to save us some money. All right, so this is the rebate first. You have G of the F of P function. The F of P function is just P minus 200, just bring it down. And now we want to plug this into the G function. All right, so take this, and it's an algebraic expression, then plug into the G function. Well, the G function is 0.80 times P, but we want to change the P to P minus 200. Okay, so here's the expression for the rebate first, then the discount. Now, which one's a better deal? We have variables involved in here, so let's just, plug in numbers. Let's pretend, okay? Let's let the price of our computer be that $1,000, okay? So let's let the price of the computer be $1,000, and let's compute and see which one is truly the better deal. If the price of our computer is the $1,000, then discount first, then rebate is going to give us what? 0.80 times 1,000 minus 200. Okay, so 80% of 1,000 is 800. When you take 800 minus 200, you get $600. Okay, so if you do the discount first and then you take the rebate after the discount, you're paying $600 for your computer. Okay, what if you take the rebate first? Okay, so we remember our computer's $1,000. So what if you do 0.80 and you multiply that, you get 1,000 minus 200. What if we do it this way first, okay? Order of operations, we have to evaluate inside these parentheses, okay? So we're taking 80% of 1,000 take away 200 is 800, okay? And then when you take 80% of $800, it's $640. All right, so it's $640 this way. All right, so F composed with G is taking the discount first, then the rebate, because you work from the inside to the outside. So if you take the discount first, then the rebate, your computer is $600, okay? If you take the rebate first, then the discount, you're paying $640, okay? So what is the best deal here? Well, the best deal is make sure you tell the salesperson and watch them good. You want to do the discount first and then subtract the rebate off the discount. And that's going to get you the best deal, okay? So I hope this helps with your just understanding of functions, the concept of functions, one-to-one correspondence, all right? Best wishes to all of you in your endeavors in mathematics, and thank you for watching.